Yeah, so let me just tell you let me, because it was a fairly long problem, so let me just kind of now, after written it out, explain to you what we did in a sort of a summary way, yeah? So this was number 4, and it asked to seek power solutions of the given differential equation about x0. So basically your power series is centered at 0. And then it asks to find the first 4 terms in each of, so we're going to get two, and then to find a recurrence relationship between the coefficients, okay? And then it asks to find the first 4 terms in each of the 2 solutions, y1 and y2, and basically evaluating the Wronskian to prove that this is a fundamental set of solutions. Okay, so the way we start this is we assume solutions of the form of a power series centered at 0. Yeah. So that's summation from n equals 0 to infinity a of n next to the n. Okay. And then we take derivatives of this. We take first derivative, we take second derivative, because we need second derivative in the differential equation. And the way we differentiate series is the same way we differentiate anything else. So x squared becomes 2x, and here x to the n becomes n times x to the n minus 1. And it remains a series. The only difference is now, because when n is 0 here, what's your first term in the series? When you see, when n is 0, let me switch colors here. When n is 0, your first term here is what? A0, right? So when you take the derivative of this, that's 0. So now your first derivative starts at n equals 1, because you already lost a term when you differentiated a0. And then y double prime will be the same thing. You differentiate x to the n minus 1. Right. And then you bring the n minus 1 down. So n times n minus 1a, n times x to the n minus 2. And again, here you lost the first term, because when n was 1, this was n 1 times a1. 1 times a1, the derivative is 0. So you lost another term. So yeah, the series now starts at 2 instead of 1. So every time you take a derivative, your series progresses by 1. So it starts at a term, 1 term later than it was before. Okay, and then then the next step is you take those derivatives, you plug them into the series.
That's not one term. Is it 1 term later, or is it just basically it has to? There's a minimum n value for a given derivative.
Well, I mean, technically, I'm saying that like one term vanishes.
Yeah, I'm saying like if it was y prime.
Like here, for example, when n is 1,
you can also have.
You're gonna get
y of n is 1.
When n is 1, you're gonna get a1.
Yeah.
And the derivative of a1 is 0, so it goes away.
Yeah.
Okay, and then you take those derivatives and you plug them back into the differential equation in a series format. And when you do that, you get one series, which is y double prime plus k squared x squared y, which we assume to be the solution, no, equals 0. And then what we did is we went and we brought this x squared in, and we worked on this one here. What's this one? So we expanded a few terms, yeah? So we said this is x squared times, if n is 0, then you get k squared a0. If n is 1, you get k squared a1x, etc., etc. We expanded a few terms. Then we foiled the x squared in. And when we foiled the x squared in, we got a squared a0x squared plus k squared a1x cubed, etc., etc., till the end. No? And now what that seems to indicate, we can write a more general term that this is a series that starts at 2, no? Yeah. With k squared, and when x has a power of 2, the coefficient is a of 0, which means the coefficient is 2 less, or 2 earlier than the x. So this is a of n minus 2. Yeah? And now we said, okay, fine, since this is a dummy variable, let k be n minus 2. Okay? Because what we're trying to do is we're trying to make those two series start at the same end so we can combine them together.
Yeah.
So we said let k equals n minus 2, and then we made the start at k equals 0, and wherever there is an n, we went and we plugged k minus 2. Yeah, we shifted the index basically, because from this you can say n equals k plus 2. Okay, and we went and we plugged it in, and after we did the shifting, we got two series that are still not starting at the same place, but at least they have a common x power now. They're both x to the n. And then what we did next, we said, okay, fine, then we're going to absorb two terms from here, n equals 0 and n equals 1, from the one on the right-hand side. So when n is 0, you get 2 times 1 times a2, plus when n is 1, you get 3 times 2 times a3 times x, plus the remainder of the series that's now starting at 2, because we already took the n equals 0 and then equals 1 out. And now we can put these two series together. We can put this together with this, because now they both have x to the n and they both start at x equals 2. So we did that. We factored x to the n out, put everything in. Yeah, plus 2a2 plus 6a3x, which are the terms that came from n equals 0 and n equals 1, equals 0. And now for this sum to be 0, the coefficients have to be 0. So we set the coefficient a2 equals 0 and a3 equals 0. And also the coefficient here, which is k squared a n minus 2 plus n plus 2 plus n plus 1 a to the n plus 2 equals 0. Now this is the recursive relationship that the question is asking about. No? This is the recursive relationship. In other words, it's the relationship that gives you the relationship or how the coefficients are connected. Coefficients at different places are connected. So a of n plus 2 is related to a of n minus 2. So one term is related to, well, one coefficient is related to the coefficient that comes 4 places after.
Yeah.
And then again, we shifted the index here just to make it look more appealing. We said, okay, let n minus 2 equals k, then n is equal k plus 2, then this becomes a of k plus 4.
Yeah.
No? And this becomes a of k. And then we said, okay, fine. Then we went back, and again, it's a dummy variable, so we called it n, just so we can go back to n. And now we calculated a few terms. So when n equals 0, we plugged it in. When n equals 1, we plugged it in for, and n equals 2. And here we got 0. How come we got 0? Because a of 2 is 0. If a2 is 0, if this guy is 0, then the whole thing is 0. Right. And then same thing for n3, because a3 is 0, then that's 0. And then we went on a few more terms, n equals 4. We plugged it in, the recursive relationship. And now we have a of 4, yeah? But we already know what a of 4 is in terms of a of 0. So we plugged that in, and we got a of a of 8 in terms of a of 0. And then we went and we found a of 9, and a of 9 is related to a of 5. But a of 5, we know what a of 5 is in terms of a of 1. So we went and we plugged this in terms of a of 1, and we got a of 9. Now, so what's the moral of the story here? Let me just say the main point. The main point is we are able now to obtain all the coefficients of this series in terms of two coefficients, a of 1 and a of 0. And some of them will vanish. The a6 and a7 will go to 0. So will a of 10 and a of 11. And everything in between will be expressed in terms of a of 0 and a of 1. That's why we get two solutions. One is y1 and one is y2, because now you are able to express all the coefficients of this series starting from n equals 1 to infinity, from a1 to a infinity, in terms of a of 0 and a of 1, and the ones that don't show up are just zeros. You understand? So now,
why are they 0 and then it's all of a sudden some of them they're like 0, 0,
because
4, then it's something.
Because if you look back here, when we set the coefficients here equals 0, one is a polynomial 0.
Oh,
when the coefficients are 0. So the coefficient of x to the n equals 0, which gave us the recursive relationship. The A2 has to be 0.
Right.
And the A3 has to be 0.
Yeah.
And according to this recursive relationships, some of those coefficients will be directly related to A2 and O3. So those will all go away.
Yeah.
Vanish.
And A4 doesn't have to be.
And the remaining will be because you have a relationship between a recursive relationship between one coefficient and 4 coefficients down, so that already connects all the coefficients in terms of 2 coefficients, A0, A0 and A1.
So that could happen where the first term, where like the second term of a series is 0 and the third is 0, but the fourth and the fifth are not 0.
Right. So now
that could actually happen.
That can happen, very much so. So now when you go to the assumed general solution, which is a to the n next to the n, now what does this mean? This means a1 next to the 1, plus a2x to the 2, plus a0, of course, plus a3x to the 3, etc., etc., etc. Now, we know that a2 and a3 are zeros, so there's no x squared and x cubed here.
Oh wait, A is
no?
A is an arbitrary function.
A is an arbitrary coefficient.
But
A is an arbitrary coefficient.
Should it be a function itself or no?
It might be. So yeah. So now we factored out the A of 0 because, like I said, half the terms will be in terms of A of 0 because we were able to express these coefficients as functions of A0. We factor out A0, we put everything in, and that would be 1y. And then A1, same thing. The other half will be expressed as A1. We factor out A1, we put everything in. So now basically our solution is A0 multiplied by y1 of x plus A1 multiplied by y2 of x. And we were able to answer the third question and get two solutions, y1 and y2 of that. Y1 and Y2. So our Y1 will be whatever multiplies A0 right there. And our Y2 will be whatever multiplies A1. And we were able to express those in general terms, according to that pattern that we got from figuring out a few terms from doing the, N1, 2, 3, 4, etc. And we were able to find what those solutions are. So that does it for that question. That's how we were able to characterize our two y's. This is how we do it using power series solutions. So let's go ahead and do, I think I emailed that to you, yeah?